Hi everyone. In this video, I am going to explain about what you mean by adder, different types of adder circuits, and especially how to design an in-bit ripple carry adder. Okay. So now we know that in our system, everything will be performed by our CPU, that is a processor. Processor is responsible for performing all the operations. So the CPU or the processor consisting of what? CPU consists of mainly what? ALU, control unit and some registers. So ALU is consisting of what? So ALU means arithmetic and logical unit. That means this is one unit made up of many circuits which is responsible to perform all the arithmetic and logical operations. Among arithmetic and logical, arithmetic operations are complex when compared to logical operation, as there is a concept of carry, borrow will come. So that is not there. So this logical operation is very much simple. Just and, or, not, exclusive, or shift right or shift left or rotate right, rotate left, like that. So these are the only operation logical. Using this arithmetic operation is not all the mathematical operations. Arithmetic operation means it mainly does what? Only addition, subtraction, multiplication, division. Using these four arithmetic operation and logical operation, our processor can able to do all other operations. Whether it may be logarithmic, whether it may be sine series, cos series, exponential, whatever. Calculus, everything will be done using only this operation. Now, in this video, I am going to explain about how our ALU performs addition operation, especially a simple ripple carry adder. That I am going to explain. Okay. So now, before going to that, let us take one simple example. Let us take two numbers I want to add. What do you mean by adder? Adder is a circuit. Adder is a circuit which adds two numbers. Okay, two numbers. Let us take one number called x, another number called y. Let us, I am taking x is equal to simple y, 5, y is equal to 2. X is equal to 5 means because our processor will do everything in terms of what? Binary. So I am writing the same 5 in the binary. So 0, I am using 4 bit. Okay, 0, 1, 0, 1. So this is 0, 0, 1, 0. This is the binary equivalent of 2. This is the binary equivalent of 5. When I add this, what happens? See, 1 plus 0 what? 1. 0 plus 1, 1. 1 plus 0, 1. 0 plus 0, 0. This is nothing but your 7. This is as expected. So this is the sum. Sum is equal to what? 7 is equal to, this is what the binary. This is very much clear, right? So it's very, very simple. Now let us take another two numbers, another example. Let us take x is equal to 7, y is equal to, let us take some 5 or 6, whatever you can take, 5. So now again this 7 I am writing in terms of binary, that is 0, 1, 1, 1, and 5 is 0, 1, 0, 1. This is my 5. Now what I am adding, see, these are the bits, okay, these are the bits of x and these are the bits of y. So I am going to write the same bits as this as my x0, this is my x1, x2, x3, bits, individual bits. Similarly, these are the bits of y. I will call this as y0, y1, y2, y3. Okay. Now what I will do, I am adding first time. See, this is my, these two bit added together, these two bit added together, these two bit added together, these two bit added together here. Now similarly, now I will add these two, I will add together now. Okay, 1 and 1. So what is 1 and 1? So in binary, so in decimal 1 plus 1 is 2. But in binary 1 plus 1 is some bit is 0, carry is 1. So this bit is 0, some bit is 0. So sum yes is equal to 12. Okay, this is what I need to get. Now 1 plus 1 is 0 and it is generating carry 1 to the next stage. Okay, this is as see, let us say I'm adding 7, 8, 7, 4, 2 and then 6, 9, 8, 9. Assume these two are the numbers. Let us take ordinary what? Decimal number. 2 plus 9 is what? 11. And it produces carry to the next one. So 1 plus 4, 5. 5 plus 8, 13. Again it will generate carry to 1. So 8 plus 8, 17. It generates carry 1. So 9 plus 6, 15. So it generates 1. So this is my answer. This is my sum. Okay, so similarly, same way, always will come from the LSB. We are adding, how we are adding in general. So we are adding again from the LSB. And when I added these two bits, some bit is 0 and it produces carry to its next stage. Now, I am adding, actually I want to add these bits. These bits I need to add. Now, when I am adding these two, 1 plus 0, 1, and I need to add a third bit. The third bit is the carry generated in the previous stage. Okay, see, this is my what? First stage. This is my second stage. This is my third stage. This is my fourth stage. So when I'm adding second stage 1 plus 0, I need to add the third extra bit, that is the carry generated in the previous stage. So this is 1 plus 0 is 1, 1 plus 1 is 0 again, and this stage produces carry to the next stage 1. Now I need to add, actually I need to add these two bits, and again 1 plus 1 is some bit is what? 0, that will be added with 1. This is the carry bit generated in the second stage. Now I am adding the third stage. When I am adding the third stage, I need to add these two bits, and this is the carry extra bit generated in the previous stage. Okay, now 1 plus 1 0, 0 plus 1 is 1, and carry is generated to its next stage. That means third stage generates the carry. Whatever the carry generated in the third stage is given as input to the next stage. Now again, in the fourth stage, I am adding only what? These two bits. 0 plus 0 is 0, and 0 plus 1 is what? 1, and this stage is producing carry what? Nothing, 0. So this is my what? Sum bit. This is nothing but 12. My answer is getting correct. But the concept is what? When we get this example, in all the stages, first stage, second stage, third stage, fourth stage, we added only 2 bits at a time. Always in all the stages I added only 2 bits. There is no carry generated in this example. But so circuit which is to add only 2 bits at a time is called what? Half adder. Half adder. But when we take this example, see, this is not always the case. We don't know which stage is going to generate what carry to the next stage. So carry may be generated at any stage. We don't know. So it is not always possible to add 2 bits. Sometimes we need to add this extra bits. This extra bit is a third bit, or extra bit is a bit generated in the previous stage. See, this is the one I am adding in which stage? Second stage, but it is generated in the previous stage, first stage. Similarly, when I am adding in third stage, these two, third stage, I need to consider this one, and this is the one carry generated in the previous stage, second stage. So we don't know which stage is generating carry to the next stage. So here we need to add 3 bits at a time. Initially only 2 bits, but afterwards 3 bits I need to add. So that cannot be done by using half adder. So half adder can add only 2 bits at a time, but we cannot use half adder always, because we don't know which stage is going to generate the carry to the next stage. So we have to add what? The 2 bits or the 2 numbers and the carry generated in the previous stage. That means we need to add 3 bits at a time. So we need to use a circuit called what? Full adder. Full adder. So full adder is a circuit, adder circuit again. So it will add 3 bits at a time. Okay, 2 bits are the, 1 bit is from the x number, first numbers, while another bit is another bit of the another number. The third bit is the carry generated in the previous stage. So that was the full adder. Now let us write for this the truth table. So now in this stage, what I added x naught and y naught, and initially carry is what? Always initially carry is 0. There is no carry in the first stage, because this is the first stage I am adding. There is no carry. So initially carry I will say C naught. I need to add these 3 bits. So instead of writing C naught here, so I will write C naught here, because always carry what the third bit is generated in the previous stage. So that's why I am writing it instead of writing here. After adding these 3, I will get what? Some bit S naught, and it produces carry to its next stage. That is, next stage is what? C1. So in general, what I can write, so in similarly, I need to write what? X1 and Y1 I need to add. When I'm adding X1 and Y1, so this is the one generated in the previous stage. So that is the C1, and after adding these two, I'm adding S1 I'm getting, and it produces carry to the next stage C2. So what I can write, so in general, I'm going to write, I'm adding xi bit, that is ith bit, but maybe x0, y0, similarly x1, y1, so I may be 0, 1, 2, 3, whatever. Okay, so I need to add xi, yi with the ci, and when I add these three, I'm going to get the sum bit, ith bit, and it produces a carry to the next stage ci plus 1. This is in general. So that means now, see again, full adder is what? Is an adder circuit which is used to add 3 bits at a time. That means now here I need one full adder, here I need one full adder, here I need one full adder, here I need one full adder. Okay, so now, but now what is, let us write the truth table for sum and carry. Okay, so now sum bit, yes, okay, so first I will write xi, yi and ci. These are the 3 bits. These are the 2 numbers actually I want to add, but this is the carry generated in the previous stage. And when I add these, I will get sum I and carry generated to the next stage. Now 0, 0. When both are 0, the previously generated carry may be 0 or it may be 1. That means, see, I am taking both are 0, 0. One time I am taking constant carry 1, 0 or 1. Similarly, right, when xi is 0 and yi is 1, one time we get carry is 1 and 0 and other time 1. Similarly, when this xi is 1 and yi is 0, one time carry is 0, carry is 1. Similarly, when both are 1, 1, 0 and 1. So this is my what? The inputs. Now when these inputs, now let us add these 3. When I add it's 0 plus 0 plus 0, what is? Sum bit is 0. Carry, I am not generating anything. So when it's 0 plus 0, 0, 0 plus 1, 1, no carry. 0 plus 1, 1, 1 plus 0, 1, again no carry. 0 plus 1, 1, 1 plus 1, 0, carry generate once. Okay, sum is 0, carry is 1. So now here 1, 1 plus 0, 1, 1 plus 0, 1, carry is no. So 1 plus 0 is 1, 1 plus 1 what? 0 and carry is generated 1. Again 1 plus 1 is what? Sum is 0, carry is 1. Now 1 plus 1, 0, carry generated. So 0 plus 1, 1. So this is the truth table. So for this truth table, let us write what? K-map to get the equation for Si and Ci plus 1. Okay. So now I need to write the K-map. So for this, these are 3 input variables. For Si, I need to write the K-map. So since 3 variables means 8 combinations, I need to get 8 cells in my K-map. So 2 cross 4, that means 2 rows, 4 columns, or you can go 4 cross 2, that means 4 rows, 2 columns. Both will get the same equation. Since my equations is for xi, yi, ci, I write here xi, yi, ci, 0, 0, 0, 1, 1, 1, 1, 0, 0, and 1. Now yes, I am going to fill now 0, 1, 1, 0, 0, 1, 1, 0, then 1, 0, 0, 1, 1, 0, 0, 1. This is the K-map. Now here it is not possible to make any of the groups, so I will go for what? Making individual ones. So this is one individual group, this is individual, this is individual, individual, because it is not possible to make any group. So I will get the equation, So this is I am waiting for the Si. So Si is equal to, if I take this for this one, yes, this one belongs to what? This row, Xi, and this is Yi, Ci bar, plus, now this one is what? Xi belongs to this row, and here Yi, Ci, plus, when I go to this one, Xi bar, 0 base bar, this is Yi bar, this is Ei, plus this is Xi bar, Yi, Ci bar. This can be written as Si, can be written as Xi exclusive or yi exclusive or ci. This is my equation for what? Sum bit. Similarly, let us take equation for what? Carry. Okay, let us take carry again. So I am going to write one more k map for the carry. So again I am using 4 cross 4. You can use 2 cross 4. You can use 4 cross 2 also. xi, yi, ci 0 0 0 1 1 1 1 0 0 1. So this is 0 0 1 0 0 1. Then 0 1 1 0 1 1 1. So now I will making this as my one group pair. Okay, now this pair is belonging to what? This pair is belonging to this row. This row is xi. Now I am writing what? For ci plus 1. This is xi, and these two belongs to this column. Among these two column common is this 1 and 1. This one is ci plus. Now again I have to go to make one more group, that is what? Pair. So I am going to make this as one pair. So for this pair, this pair is belongs to this row. This is so xi, and here common is first here 1. So this is yi plus. Again I am going to make this as one more pair. For this pair belongs to only this column. Here there is no common, so I will write yici. This is the equation for what? Carry. Now if I write the circuit diagram, since it is very very simple, so I am going to take one exclusive OR gate. This is my si. So this is my xi, yi. See, simple. So that means when I pass bit of xi, suppose I is equal to 1, for example, I is equal to 1. That means when I pass x1, y1, c1, if I pass, immediately I will get after one gate delay. That means now some bit I am getting after what? One gate delay. That means as soon as, because this gate takes some time. That's what gate delay. One gate, because only one gate. As soon as pass, this gate takes some time. Only one gate takes some time. So one gate delay, I am going to get si, submit. Now let us design for this one. Now here I need to use for these two one AND gate, because xi into ci one AND gate, for xi yi for this another AND gate, and yi ci for this another AND gate, and all these gates to add to R. So I am using one OR gate. So I am getting ci plus 1. So all the outputs are to pass. Now this AND gate for this one. So this is my xi ci. This is my xi yi. This is my yi ci. So now if I pass all at a time, since all are AND gate, all will take same time. Assume each AND gate take 1 nanosecond. Assuming 1 nanosecond I will get all this output. So 1 gate delay. So here I will get what? All this output I will get what? 1 gate delay. 1 gate delay. Here 1 gate delay. Now after that, once you get all this, again this is only 1 gate. So 2 gate delay. That means I am going to get 2 gate delay. I am going to get what? Carry out. So in general, I will write one full adder as, this is one full adder. It will add what? One xi bit, yi bit, and it will take the carry from the previous stage, and it produces what? Sum bit, and it generates what? ci plus 1. So this is what one full adder. But here, like this, here one full adder, here one full adder, here one full adder. I need 4 full adder to add 2 numbers of 4 bit each. So now that I am going to write. Okay. So to add this stage, I need one full adder. So this is my one full adder. To add what? x0, y0, and I am taking initial carry 0, that is c0, and it produces what? s0, and it generates what? c1 to the next stage. Similarly, again to add this second stage, these 2 bits, I need one more full adder. So I am using one more full adder, and it will take what? x1, y1, and it is taking the carry generated from the previous stage. This is the previous stage, so it is taking this as an input, and it produces sum bit 1, and it generates the carry to the next stage. Similarly, to add the third stage 2 bits, x3, x2 and y2, I need one more full adder. one more full adder, that is x2y2, and this is one more full adder, and it is taking carry from the previous, that is c2, and this is s3. Similar, and it produces what? c3. So now finally to add the last stage, I need one more full adder, x3 y3, and this is my s4, s0, s1, sorry, this is s2, this is my s3, and it is produces c4. Now this is the circuit. Actually the one full adder means what? One full adder means this one exclusive OR gate and this one, these two together one full adder. So like this I need these two sets 4. Okay, this is 4, this is 4, this one is one full adder, this is one full adder and these two. So like that the 4 full adders. To add what? 4 bit 2 numbers. So but to add n bit what? N bit. So now I am going to write for the n bit. So n bit is same. So I am using what? One full adder. So all these are my full adders. So if you observe, if to add two numbers of 4 bit each, start with x0, y0, x1, y2, x2, y2, x3, y3. x0 last 4 bit what? x3, y3. Similarly now for this I need what? 2 bits. So this is my x0, y0, x1, y1. This is my x2, y2. Okay, not x2, y2. This is what? Last bit is what? N bit, 4 bit, it is 3. Suppose 2 bit means what? 0 and 1. 2 bit last is 1. 4 bit last bit is 3. N bit last is n minus 1. So this is x n minus 1 and this is me y n minus 1. And I am going to get what? This is my sum bit is not S1 and the last is Sn minus 1. Similarly, it is producing one carry to the next stage. This is generating carry to the next stage and this is taking carry from the previous stage and it is generating carry to the next stage. So initially what? This is C0, this is C1, this is C2, this is Cn minus 2. The last one is what? Cn minus 1 and last is Cn. Last is Cn. Okay. And this is my n bit ripple carry adder. Now we know adder, n bit ripple carry adder. This is for n number of bits. Suppose n is equal to 5 bit. This is x0, y0, x1, y2, x2, y2, x3, y3, x4, y4. If it is 8 bit, x0 to x7, y0 to y7. So now why we will call this ripple carry adder means, ripple means propagating, forwarding. That means here ripple carry. What is rippling? Carry is rippling. That means carry generated by this stage is given as input to this one. Similarly, carry generated by this one given as input to the next one. That means carry is pushed or propagated or forwarded from one stage to another. From one stage to another. Hence, this type of adder is called ripple carry adder. Okay, this is how to design n-bit ripple carry adder. Hope you people understood. Now, advantage is what? Very simple. Very simple. Just see, one full adder contains one exclusive OR gate circuit like this and one AND OR gate circuit. AND OR circuit will call AND OR circuit like this you get. But what is the disadvantage? Here, I cannot add this stage until I complete adding this stage. Even though all the bits of X is available, all the bits of Y available, we are not possible to add all the stages parallelly at the same time. I cannot add all these 4 stages parallelly. First I have to add this stage and then I have to add this stage, then I have to add, because this stage has to wait for the carry generated by the previous stage. Similarly, this stage has to wait for the carry generated by this stage. This stage has to wait, this stage, this stage has to wait for these 2 stages. Similarly, this stage we cannot add until unless it will get carry from the previous stage. That means this gate has to be depending on these 2. This has to depend these 3 previous. That means each stage has to wait for the carry generated by all its previous stages. So it is not possible to add all the bits or all the stages parallelly, even though both the number bits are we know. Because but we don't know which stage carry is generated, which stage is not generating the carry. We don't know. That is the problem. So that is the problem. See, now I told to get some bit 1 gate delay. See, here I need only 1 gate delay to generate here. 1 gate delay. 1 gate delay. Okay, now. But carry generation what? Carry generation need 2 gates. Now. So this requires what? 2 gate delay. Now, this how much it will take? So this some bit it takes 1 gate delay and plus 2. So this takes 3 gate delay. And this take what? This is 2 plus this 2. So this is a 4 gate delay. So now again to get this sum bit, this will taking is 1 and it is taking 4. 1 plus 4 5. So 5 gate delays this bit. So this bit will again take 6. Because this is 4 plus this need 2. This circuit need 2. 4 plus 2 6. So similarly, this sum bit takes 1 gate delay and this depends on the previous carry. Carry 6, 1 plus 6, 7 gate delay and this carry 6 plus it's 2, 8 gate delay. Just to add 4 bit numbers. But 4 bit number means maximum we can add 15 and 15. That's it. To add this one, we need to add this much gate delay. But in banking domains, in the complex calculation, we are dealing with 32-bit, 64-bit addition. 32-bit means like that 32 full adder circuit will be there. Last one is x31. So n bit 32. Last one is x31, y31. That means this last stage has to wait for all the previous 31 stages. See, for the first one it is 1, see some bit 1, the fourth one is 7. 1, 3, 5, 7, like this 9, like this goes on. That means for n bit it take 2n minus 1 gate delays. Suppose you have 32 bit, 2 into 32 66, 64, 64 minus 1, 63 gate delay. 63 gate delay. Suppose 1 gate delay is taking 2 nanoseconds, 63 means 126 nanoseconds. That means is 2 waiting. Not only some bit, carry will take what? N bit is 2n. 2n gate delays it will take carry. So that means 2 gate delay means 32, 64, 64 into 128 nanoseconds. But what we are expecting, whenever we click on anything, we are expecting it immediately to open. But it is taking 128 nanoseconds to generate the output. So that means it's taking too much of time. That is the disadvantage of this adder. So this is the basic adder circuit what our ALU is using at the first generation. So at the first and second generation. Now to overcome this disadvantage, we go for fast adder. That I am going to cover in the next video. So hope you people understood the concept of how to design n-bit triple carry adder. What do you mean by adder? Different types of adder like half adder, full adder. What are the equation and how to design the circuits, circuits and 4-bit full adder, 4-bit ripple carry adder and n-bit ripple carry. What do you mean by carry rippling means? Carry rippling means forwarding carry from one stage to another stage. Or carry generated by one stage will push us to another. That's it. Okay. So that we discussed. If you really like the content, please subscribe it and share with your friends and juniors. Thank you. Thanks for watching. If you have any questions, please write it in the comments. Thank you once again.